All right, so I just wanted to do a quick video talking about the key to the acid-base review number 2. A lot of it I think is pretty self-explanatory. I just wanted to make sure it all made sense. Number 1, you're just writing the equation, and remember with acids and weak bases, you always just add water. And then if it's an acid, it's going to donate its proton to the water. If it's a base, the water is going to donate the proton to the base. For sodium hydroxide, when it's a strong base, we just show the dissociation. That's why the question says write an equation describing the ionization or dissociation. So with the strong bases, we just show it dissociating. That's why it has sodium and hydroxide splitting apart. On B, we know that NO2 with a minus, the nitrite, would have a significant capacity to react with a hydrated proton. In other words, it will react with a proton because it's a base. Chloride, bromide, those are neutral. Ammonium is an acid, so it's going to donate a proton. It's not going to react with the proton. So that's why we chose nitrite. On number 2, we're just picking out the acids and the bases. So the acid is what donates the proton, the base is what accepts it. Obviously, this is a little bit different because you have ionic compounds, so you have to look at the parts. So for instance, on B, the zinc sulfide is going to be the base because the zinc, that's just an ion there. We don't really care about it. The sulfur is going to accept the proton, so that's why it acts as the base. Same goes for C, potassium cyanide. We know if cyanide's a base, it's going to accept the proton, but the potassium's just kind of a floater. It is what we would call a spectator ion, if you remember that from last year. Number 3, writing the conjugate acid. So you just write the acid form of what it shows. So you'd add a proton to each one. So that's what I did. On 4, you take away a proton because you're writing the base form of each one. Number 5, hydrochloric acid is stronger because chloride is neutral. It doesn't have any basic properties. Since cyanide can act as a base, then we know that the hydrocyanic acid must be weak. Number 6, just use the circle of life on that one. And obviously if the pH is above 7, or if the hydronium concentration is less than 1 times 10 to the negative 7th, that's going to be basic. On number 7, you have a solution with pH of 5.6. You got to calculate everything, so you're just using the circle of life, once again, 10 raised to the negative pH. Number 8, you can do 14 minus the pOH to get the pH, and then 10 raised to the negative pH will get you what you want. Number 9, it's a strong acid, negative log will get you the pH. Number 10, that's a strong base, negative log will get you the pOH, and then 14 minus that will give you the pH. Number 11, you are just doing an ice table for the hydroxylamine solution. It gives you everything you need. X is small because 1 times 10 to the negative 8th is so tiny. And then whatever X is, you do the X value divided by the starting concentration, and times 100, that gives you the percent ionization. Hopefully that all makes sense so far. Number 12, this is just a simple weak acid calculation. So solve for X. X is hydronium, so negative log of that will get you the pH. Number 13, the reason why the first proton is always the strongest is because as you lose a proton, you're left with more and more negative charge. So for instance, with phosphoric acid, you have H3PO4. Well, when you get H2PO4, you still have the minus 3 on the PO4, but now you only have 2 protons. So there's more negative charge that can hold on to the last 2 protons. When you lose another one, now you have the negative 3 charge only holding on to 1 proton. So each time it's going to hold on to that proton more and more strongly. Number 14, A, the difference is so big that you don't really have to worry about it contributing much to the hydronium after the first one. To get the pH, just do your ice table of the first proton. You had to do the quadratic, but then X is hydronium, so just negative log of that will get you the pH. On 15, you're just looking at the cations and anions. Remember, the cation, that is the conjugate acid of a strong base, is neutral. The anion, that's the conjugate base of a strong acid, is neutral. And then you just can kind of go from there. So A, both of those are neutral. On B, ammonium is acidic, but NO3 is neutral. On C, sodium's neutral, but CO3 is basic. And then on D, rubidium, though we didn't talk about it, we typically consider that neutral, and fluoride is basic, so that one would end up being basic. 16, you had to do an ice table to get the hydroxide concentration. Then you can get the pOH from that. 14 minus that will give you the pH. On 17, the reason why HOCl is an acid is because the Cl is very electronegative, whereas sodium is very electropositive. That means that the Cl helps weaken the bond between the hydrogen and oxygen, whereas sodium does not. So the HOCl is going to be an acid. On 18, I drew it out for you. The stronger acid is going to be the sulfuric acid, obviously because you memorized it as a strong acid, but also because it has more oxygens. So that's how that works out. Number 19, if you draw it out, you can see the hydroxide has an extra pair of electrons, so it can donate those electrons to the proton, which makes it a Lewis base. The hydroxide would be a Lewis base, but it's also a Bronsted-Lowry base because it accepts the proton as that comes along. So that's how that went. On number 20, ammonia is going to be the electron donor, so therefore that's going to be the Lewis base, and then that makes silver the Lewis acid. 21, you don't need to know this for the test, I just wanted you to be familiar with it. That's one of those complexes. Zinc in some situations could act as a small highly charged metal, so I just wrote out that equation for you, but don't worry about that too much. I hope that helps. If you have any questions, please email me, let me know, and I will do my best to answer.